We're going to go through the ideas of splitting second-order ordinary differential equations into two coupled first-order ordinary differential equations. I'm going to do it first explicitly, not writing any functions, just making it clear how it works, and then show why it's a good idea to write it in a particular way that we've discussed in the lectures. So to start off with, we have the simple harmonic oscillator equation that I've written here. And the first thing that we're going to do in terms of the formal maths is split that into two. So if we think about the standard definition of velocity, v is dx by dt, then with this first equation here, we can move the m to the right-hand side, and then we can rewrite the SHO equation, the simple harmonic oscillator equation, as a first-order differential equation in terms of the velocity. So let me just add that and show you what that looks like. So here's the first-order equation. You've got dv by dt is minus kx over m. And then we can use this equation above, dx by dt is equal to v, and we now have two first-order simple harmonic oscillator equations, though they are, two first-order ordinary differential equations, though they are now coupled. And what that means is you cannot solve one without the other. You have to solve them together. So if you're doing a numerical integration, you can't just simply go through this equation solving for all values of v and then go through this equation solving for all values of x, because then they won't work that way around. Let me show you that. So what we're going to do is we're going to expand the derivatives in terms of a simple forward differential equation, which is how you get the Euler approach. So if we're writing, for instance, dx by dt is x of t plus delta t minus x of t divided by delta t, then we can rewrite these two equations as I've done here. So you get x of t plus delta t is x of t plus v of t times delta t, and v of t plus delta t is v of t minus kx of t over m times delta t. And I've put in the times here explicitly to make it clear. So to get x at t plus delta t, we need v at t. To get v at t plus delta t, we need x of t. So if we were to try and do this without the coupled equations, we would get nowhere. Let's turn this into code. So I'm going to start off just by pasting in some very simple parameters here. The simple harmonic parameters, I'm assuming SI units, so the mass is 1, the spring constant is 1, the time step is 0.01. We'll look at that in a moment. I'm defining a total time of 10 because I've got m and k both 1. We know from very simple maths that the simple harmonic oscillator will go through a single oscillation in about 6.28 seconds. That's 2 pi seconds. So 10 will give us more than one oscillation. And I create an array of time steps. Okay, so that's just written that. Let's put together some initial conditions and some storage. So what we're going to do here is we're going to say that x is equal to 1, so that's the maximum displacement at t equals 0, and v at t equals 0 is equal to 0. That's why I say it's the maximum displacement. We'll need some storage for all of our positions, and now let's iterate. So we're going to start off by setting the initial position. So x at time 0 is equal to x0, v at time 0 is equal to v0, and now we're just going to iterate for I in range n steps minus 1. And you see why I've done minus 1 in a second. We can say x of I plus 1 is equal to x of I plus v of I times dt. And just compare this equation here, this line of code, with the equation up here for x. They're identical. And then for v, we have v of I plus 1 is equal to v of I. And if we look at the equation, there's v of t plus delta t, that's v of I plus 1, is equal to v of t, that's v of I. So now we need a minus, and I'm going to have k times x of I, that's kx of t, divided by m, and then that's all going to be multiplied by dt. So that's just turning this simple difference equation into code. So we'll run that, and now we need to plot. So I'll do plt.plot of time comma x. Let me just check that that works. That looks reasonable. If I put a grid on there, then I can see that actually, okay, the amplitude is getting bigger. Now, physically, we know that's nonsensical because we're not putting energy into the system, but that's just an indication that this time step is too big. We'll come back and look at that in a second. Let's put some labels on our graph. X label should be time, the y label will be displacement. And we'll put a title as well. Once I've fixed the y label command, title is going to be, let's say, motion of the SHO from Euler. And actually we'll put in the dt, with dt is equal to dt, but now we need to make that a formatted string. That's what the f you put outside. And let's see what happens. Yes, okay, so we get the title correct. So the motion of simple harmonic oscillator using the Euler approach with dt as 0.01, we can see that we're going too high. What happens if we make that smaller? Let's make it 0.001. And we can see that at least on this time scale, that now obeys the expected behavior. Okay, so that's all very simple and easy, but let's just consider a little bit more carefully. If we had, instead of x here, if we had a vector r, then we would have two components. And the velocity would have two components. And so this simple first order ODE would be a vector equation. And what we do when we're solving second order ODEs is we treat the different components of the first order ODEs as a single vector. So if we combine x and v into a single array, which is a sort of a pseudo vector, then we'd have x and v as the same array here. And then we just need to make sure that whatever was on the right hand side here multiplied by dt had two components in it as well. Let's try writing that just so I can show you what I'm talking about. So we're going to define the SHO derivative as being a function of y comma t. We're going to put y and t so that it's general. So I'll put a docstring, evaluate derivatives for position and velocity for the SHO with both quantities in the same array. And I'll put some inputs. So input y is going to be an array containing x and v at present time step. That's quite important. That means it's at time step I. T is going to be time not used here, but included for generality. Because in general, we are going to want to have that kind of thing there. And then we need to talk about the output. And the output is going to be dy, which is an array containing dx and dv. And notice we're assuming that x and v are embedded in y in that order, and therefore the array has to have the same order. So let's make this nice and clear. We'll say that x is equal to y of 0, v is equal to y of 1. Then we can calculate dx is equal to v, and dv is equal to minus k times x divided by m. We're assuming those exist outside. I should probably put that in the docstring, but I'm not going to do just for now to save time. And we'll return a numpy array of dx comma dv. So that's a simple function that just embeds the calculation of these terms here on the right hand side of the basic equations. If we go back up here, so dx by dt, okay, the way I've written it is the left hand side, but here it's the right hand side. So now what does this enable us to do? Well, it enables us to do the following, so that y is equal to numpy.zeros, creating some space. Now it's going to be a two component array, and we're going to have a size of n steps, comma 2. The 2 is because I've got x and v. Y at time step 0 is going to be a numpy array of x0 and v0. And now I'm going to iterate just as before for I in range of n steps minus 1. And I'm going to say that y of I plus 1, oops, let's take that equal sign out, is equal to y of I plus the simple harmonic derivative of y of t of I, comma, time of I, and I'm going to multiply that by dt. So that's much more compact than we've got here. We haven't got the explicit arrangements here, and it's something that we can use for any dimensionality and actually any order of ordinary differential equations. So if you had a fourth order ODE, you could use this same set of loop to do exactly that. So it's a very, very general thing. I'll show you an example of that in a minute. So I've run that. What happens now? Let's do plot of time comma y. Now let's think about the indexing. The first index is the time, so I want all of those. The second index selects between position and velocity, so I'm going to choose 0 because I want the position. Let's just put a little note, plot position. And let's see what happens. Well, look, we get exactly the same thing as we had before. And I'm just going to copy those labels to make sure it's nice and clear. And yeah, we get the same thing. Now, we would expect to get the same thing, but it's just reassuring. So finally, let's think about a slightly more interesting example. Let's think about a 2D harmonic oscillator. I'm going to say that the initial position is going to be a numpy array of which can be 1.0, 0.0. So that means we're starting at position 1 on the x-axis. The velocity is going to start as numpy array of 0.0, 1.0. Okay, so that means that we're starting on the x-axis, but we've got a velocity in the y direction. If you think for a moment, you should understand what kind of motion we're going to get in a moment. Let's create an array to hold our results. So we're going to be numpy of zeros of, now let's just think about this, up here where we had a one-dimensional problem, we had a size of n steps, 2. We could have done n steps, 2, 1, so that you've got time step, you've got position or velocity, and then the 1 would indicate that actually there's only one dimension. So down here what we're going to do is we're going to say n steps, 2, 2. So we've got time, position, or velocity, and then x or y. So those are the 3 different indices, and we'll see how we use those in a moment. So y2d at time step 0 is now going to equal a numpy array, which puts together, let's put this in square brackets, x2d 0 and v2d 0. Okay, so that's actually almost exactly what we put here for y of 0. So almost no change at all. And now we'll do for I in range n steps minus 1, y2d of I plus 1 is equal to y2d of I plus the right-hand side, no, what was it called? It's SHO derivative, there we are, of y2d of I, comma, time of I times dt. So you see that we've changed the dimensionality of our problem from 1-dimensional to 2 dimensions, and the only thing we have to change is the input of the arrays. The actual argument here is the same. We haven't had to change this right-hand side equation. So this starts to show you some of the power of this approach. That ran. What do we expect to see? Well, let me first of all start by plotting x against y. So plt.plot, I want the, let me just put a little note here, x versus y. So I want to have y2d of, I want all time steps, so that's colon. I want position rather than velocity, so that's 0. And then I want the first variable to be x, so that's 0. And then I'll put y2d of colon, comma 0, comma 1. Okay, so that's selecting the x and the y components of the position. I'm plotting x against y, and what do I get? Well, look at that. Well, okay, so it's squished. Let's change the aspect ratio. It's a circle. Does that make sense? Well, let's plot the x and y components together, against time rather than together. So we want y2d of colon 0, 0, and I want plt.plot of time and y2d of colon, comma 0, comma 1. And let me plot that, and we see that the x and the y components follow cosine or sine sinusoidal curves, which are a factor of pi by 2 out of phase. This maybe shouldn't surprise you. So let me just put in here a label x and y, and I'm going to copy my set of notations here as well so I can see them. And I'm also going to put in a legend. Okay, So now we can see that x starts at the maximum point where y starts at 0, and then they carry on. And this very characteristic sinusoidal motion, but with a pi over 2 phase difference between x and y, is absolutely standard for circular motion. You will notice if you look closely at this motion that you can actually start to see the deviation away from perfectly circular, even for a time step of 0.001. And that shows you why the Euler approach is perhaps a little dangerous to use. So what I've intended to do here is to show you that by starting from a second order differential equation, breaking it down into two coupled first order differential equations, while you can implement it like this, just explicitly with the equations and everything together, it perhaps is a little more efficient to write a right-hand side function in a general way, and then to make the loop, which of course could also be a function, in a general way. And I've shown you that we can go from a single one-dimensional problem to a 2D problem with almost no change to the code at all.